So we're going to walk through the Ion-implanter example in the Kامسول model library. We'll start with a 3D geometry. We can find the free molecular flow interface on the fluid flow branch in the rarefied flow section under free molecular flow here. And then we can, once we've selected that physics, we can click next. Finally, we want to do a stationary study. Click stationary and click finish. So we're going to start the model by adding some parameters. I'm going to bring these in from a file on my desktop. And we get a few predefined parameters. We could type those in manually too if we wanted to. We've got various parameters. The first one is for theta, which is the angle between the wafer normal and the beam line. And then we've got a couple of parameters for different pump speeds in the vacuum system, so we can conveniently change those if we're interested in them. We're going to bring the geometry in from an existing Kامsól file to save a little time. And the geometry sequence starts off with an import from an external file. That could be a CAD file, and that just shows the exterior surfaces of the vacuum system. Then a work plane is defined, and you can see from the settings here that this particular work plane is defined specifically to be at the correct angle to the beam line, depending on what value of theta we've chosen. So if I go into the parameters and choose theta value of 0 and then head back to that work plane, you'll see the work plane is now vertical, and similarly if I go back and change it back to 30, our work plane will go back to the way it was before. On the work plane, a very simple geometry has been drawn out. It starts off with a circle, which has been used to represent the wafer, and then surrounding that is just a square which represents the carrier for the wafer. That work plane is then extruded. You can see that if I change this to wireframe to produce a three-dimensional object, and then that three-dimensional extruded object is subtracted from the geometry as a whole to produce a domain which just simply represents the region in which the molecules flow. So if I change the settings here, you can see there's a sort of hollowed out region in the center in this domain. Okay, now we need to set up the free molecular flow itself. On the interface level, we can change some settings that determine how accurately fluxes are computed, but we'll just leave those with the defaults, which are usually fine. We have a molecular flow node which is on the whole domain that we're modeling in, and on that in that domain we can set the temperature of the flow as well as the molar mass. So we'll go ahead and change the mean molar mass to 2 grams per mole because we're interested in the flow of hydrogen for this particular model. Now by default the boundaries are assigned to the wall boundary condition, which just sets the outgoing flux J equal to the incoming flux G. So all the molecules are absorbed and then diffusely readmitted by the wall. But we're interested in having an outgassing wall where additional molecules are added to those that strike it. So we're going to choose the outgassing wall boundary condition, and then to select the boundary that we want to apply this to, we just simply left click until it's highlighted and then right click and you can see that the boundary of interest turns blue, so our wafer is outgassing. We don't want to specify how much is outgassing using a molecular flux. We could choose a number of options here. We want to specify the number of SCCM. You could choose a mass flux or the total mass flow if you wanted to use those options as well. So we're going to have 30 SCCMs of hydrogen coming off our wafer. We also need to set up the pumps. So we have a vacuum pump boundary condition. There are various options once again to specify how the pump is operating, but we're going to use the pump speed option and type in the parameter that we set up earlier to set the value of the pump speed. We want to apply the pump, the turbo pump on this boundary, and I'm going to add another vacuum pump boundary condition using the duplicate feature. Move that selection and add a new selection and change the pump speed to the pump speed cryo, and then I'm going to repeat that process. Duplicate, change the selection, duplicate, change the selection, duplicate, change the selection. The reason I've done this is because the pump speed boundary condition computes an integral over the surface of the pump to work out the area, and so we want a separate selection for each individual pump. For the mesh, we can use the default mesh that's controlled by the physics in Comsol, but we're going to just make the mesh slightly finer and just take a look at how that looks. So you can see the mesh is actually pretty reasonable for this demonstration problem.